What kind of things cause melting? Well, to go back to our kind of water and ice example from last week, if you wanted to melt something, you heat it up because you have heat. You have a gas stove, or you have a, something, a candle. You can heat something up. Well, there is a lot of heat deep inside the earth, like the inner core, the outer core, and all that. But really, there's, it's already causing rock to melt. As far as the Earth's crust, there's not a whole lot of additional heat available sufficient to get most rocks to melt. We need to do some other things, and there's a lot of other ways that materials can begin to melt. So if the crust and the mantle are solid, remember the mantle is like a taffy, like a soft, movable solid, but it is solid. It's not like the deeper we dig into the crust of the earth and then we get to the mantle where all of a sudden we have all this magma. That's not the case. So where does magma come from? If all that material is solid, as we know, where does magma come from? So we have a few different processes we're getting into today. So magma is going to form first from the upper mantle or the lower crust, again, which is solid. But we need a few things to happen. We need, or one of a few things. Partial melting can occur, and this is something we don't see with a lot of materials that we're familiar with, like ice, for instance. You can't partially melt ice. Yeah, you can melt just a little bit of it, or something like that, but that's different. We're talking about, remember, we have a rock that is made up of lots of different components. It's made up of olivine and augite and feldspar. It's made up of all these different things which have cooled and solidified at very different temperatures, right? The same is going to happen back the other way. So our Bowen's reaction series, where we first solidify olivine and then augite and hornblende and feldspars and so on, we're going to go back the other way as a solid rock that's made up of these things begins to melt. So our picture here is showing us a lot of different igneous intrusions or plutons. So these are, our magma chamber is kind of this big area here in red. And as magma, which is molten, right, rises to the surface, conduit for a volcano. And that magma chamber itself may begin to harden and solidify on itself and can eventually be exposed and end up being a mountain system like the stock over here, where we have this part exposed at the surface. That can happen too. So this is what's going on underground. We have, all this magma going on, and we just have one volcano here in this image. A volcano is just the part that we see, but all this is happening. So this partial melt, if this is going to be, a lot of different kinds of minerals mixed together, is going to begin to rise to the surface and fuel different kinds of volcanoes. So how does that partial melt happen in the first place? So in lab, I believe, you are going to be looking at a temperature pressure diagram. So over here along the x-axis, we're looking at temperature going from cooler to hotter as we go left to right. Along the y-axis, we're looking at depth. So we're going from shallow, and this up here, let me grab a pen, is going to represent the surface of the Earth. Right? Shallow, we're at 0 kilometers below the surface of the Earth. So this is the surface. I can even draw a little person here as if you're walking around on the surface, if that helps you. Similarly, along the other kind of y-axis here, I guess, is pressure. So as depth into the Earth increases, so also does pressure. So we're seeing both of those things happening. So let's look at our chart a little bit. You'll be looking at something like this later on. But we have a rock here, this black one, and this little circle here. I'll just put an X. And a few things are happening here. We need to go ahead and get it to melt. And to get it to melt, we need it to cross this black line, this thick black line. So right now, it is down in the, I guess, the asthenosphere. We have the lithosphere. It's getting shallower. And it is solid because it's in kind of this pink area. And this is going to be the solid material. As it moves across this black line, it's beginning to melt. And then finally, this thinner black line, that means that it's a complete melt. So we have solid rock. That's what solidus means there. So the solidus is this line here. Geotherm refers to the fact that as we get deeper and deeper into the Earth's crust, it gets hotter and hotter. That's what the geotherm represents. So anyway, we have this rock at point X that is solid. One of three things can happen to get this to melt. First thing you might think of, because of cooking and just because of day-to-day stuff, is adding heat. That can happen. And if heat is added, that means that this point X is going to move over in area A. So we're going this way because we're staying at the same depth and therefore the same pressure at about 5 gigapascals, about 150 kilometers deep, whatever. But what's changing is temperature is rising as we go from left to right. So heat is being added. And that does happen in some places in the Earth's crust. But that's not the dominant way that rocks can begin to melt. And that's also not the most fun, interesting way either. What else can happen? Well, as this material at point X rises, so think about some plate tectonic situations that may cause the solid rock to begin to rise. Okay, what kind of plate tectonic boundary could that happen at? Talk about that a little later. The temperature can stay the same. This temperature isn't really changing. So we're still staying in about the 1400 or so degrees Celsius range, not really changing temperature, but as we go up, what is changing? Pressure in depth, depth and pressure are together. So pressure is decreasing. This is a very special process called decompression melting. And even if temperature is not sufficient enough to get that rock to melt, beginning to release some pressure on that rock can allow it to go ahead and expand, allow those atoms to go ahead and begin to move around, and that can go ahead and encourage it to become a liquid. A lot of rock is solid, not because it's cold, deep, deep, deep in the earth, but because it's under too much pressure. And for a rock to turn into a liquid, for a rock to melt, those atoms need to spread apart and move around. Rock is more dense as a solid than it is as a liquid. Now, that's the opposite from water, okay? The ice cubes float in a glass of water. The reason why is because ice is weird. Water behaves weird. It's a very unusual material. It's opposite of rock in a lot of ways. And as water freezes, ice takes up more space. Those molecules are forced further and further apart. So how is that related to this if it's the opposite situation? Well, the really cool thing is that deep sea submersibles, these submarines that go down into the Marianas Trench and stuff, they detect temperatures of water that are way below freezing. But it's water. It's the ocean water at the bottom of the Marianas Trench, well below 32 degrees Fahrenheit. Why is it a liquid? Because pressure is too high for those water molecules to move apart to become the solid they want to become. As it reminds us that pressure, again, like from last week, is at least as important as temperature when we're talking about great, great, great depths, whether we're in a deep sea submersible at the bottom of the sea, or whether we're going deep into the crust and even the mantle of our planet. Pressure is going to be super important and is going to play a big role in whether or not something hot like rock goes ahead and melts. Okay, and what's the last thing we could do? So we can add heat, we could lower pressure, or we can introduce a fluid, particularly water. And water is going to allow molecules to move around. That means that, okay, once again, we can start to melt, because for rock to melt, molecules need to spread further apart, and water or another fluid, maybe carbon dioxide, sulfur dioxide, a lot of different things in here, can go ahead and encourage that. So to kind of summarize, I know this is a lot of stuff, and again, it's happening deep inside the earth. It's hard for us to see and really imagine this sort of thing. Luckily, we can study a lot of this in a lab, though. But when we're talking about something surpassing the threshold at which it goes from a solid to a liquid, we're not just talking about temperature. We're talking about pressure, and we're talking about fluids that, in both of these things, can allow those molecules of that solid rock to open up and move around and therefore become a liquid, even if they're not quite at the right temperature to become a liquid. Water and lower pressure can get that to happen. So let's take it to plate tectonics then. That's exactly what we see in the Earth. We don't have a whole lot of extra heat lying around to go ahead and get solid rock to melt. There is one situation where that does happen. So that happens at our oceanic hotspots. So hotspot volcanism there, like a hotspot volcano like Hawaii, is a really good place where we have our solid oceanic crust, or well, Yellowstone continental crust, right? But we have our crust, and it's over top of a mantle plume where we have a lot of heat coming up out of the mantle. Okay, that's pretty easy. It's pretty basic, just adding heat, simple stuff. But let's go back to our other one. What about pressure is being lowered, okay? Or decompression melting there. How can that happen? So we have solid rock, and as it rises closer to the surface, pressure lessens, allowing those molecules to expand and open up. So let's think about our other plate tectonic boundaries now here. Divergent plate boundaries and convergent plate boundaries, or subduction zones. Where is a good location where we have solid rock, not magma, solid rock rising and beginning to experience less pressure? It stays hot, it doesn't cool down, but it stays hot and pressure is lessened. It's going to be at our divergent plate boundaries here. So again, pressure is lowered at these locations as we have our, it says rising magma, but really down here, we're talking about solid rock, solid mantle peridotite, and it doesn't melt until it begins to rise. So we'll get the partial melting of that. Okay, the third one, water. So how do we get water to go ahead and get down into the rock? And that's going to happen at subduction zones. So whether we're dealing with a continental subduction zone, where we have oceanic plate diving down under a continent, or whether we're dealing with an oceanic plate diving down under another oceanic plate, either way, this oceanic plate has been at the bottom of the sea for probably millions of years, 100 or more million years. It's full of water. It's full of all sorts of stuff that we'll talk about today, but it's full of water. So as this oceanic crust is descending, yeah, it's getting hotter, but it actually doesn't get hot enough to melt. We can get super, super deep and it's still not really hot enough to melt due just to heat. And in fact, think about pressure. Pressure is increasing as this rock is buried deeper and deeper and deeper. There's a lot of things against this rock needing to melt or being able to melt, except that we have water. So water is going in here. It's allowing this wet rock to go ahead and melt at a lower temperature than it otherwise would. So water is a huge part of volcanism, not just because of the melting, but because of some other things we'll get into in a second. Okay, so, here we go. We'll get into that now. Water doesn't stop there. Water is also going to get down into our melting rock, and it's going to boil because water is going to heat up at a much hotter temperature than it takes for water to become a gas. It's under a lot of pressure though. Ooh, we have steam, we have water vapor, right, our steam, we have it pressurized. That's starting to, and we have magma going on too. That's starting to sound like a dangerous situation, and it is, because this is going to build up a lot of pressure. So all these gases, and not just steam, but some other things we'll get into in a second, but mostly steam. About 90% of the gas that erupts out of a volcano is water vapor, it's steam. So all this water vapor is going to build up pressure, build up pressure, build up pressure behind this magma. And that's what causes subduction zone volcanoes to be very, very explosive. We don't have to worry about this with Hawaii because we don't have a way for the oceanic crust to drive water down into, under the Hawaiian Islands. They're just melting because of conduction, basically. Very simple, heat transfer, not a big deal. But in subduction zones, like the Philippines, like Indonesia, like the Cascade Range of North America, like the Andes, we're dealing with water being injected into this situation, building up a lot of pressure as it becomes steam behind magma. So we get explosive behavior. So that's pretty cool. But what other materials can end up in our subduction zone? Again, it's not just water. We've had this oceanic crust sitting at the bottom of the sea for 100 million years or more, and it's got a bunch of junk on it. Okay, so it's saturated with water, of course, but we have some sediments. Let's think about what kind of elements we can have here. So sediment from the ocean. So I ask students like, what's at the bottom of the ocean? And people say dead whales. Yeah, we're looking at carbon, and not necessarily just from whales, but from life, mostly from plankton, like this guy, right? He's a plankton. No, the plankton actually looks like this. But anyway, the oceans are full of plankton. Those are living organisms. So we have carbon. And it's amazing because you go to like Mount St. Helens or something that's pretty far inland, and you sample that, and you end up getting a carbon that has the signature of life. It obviously came from the cooking, I guess, of living things. So that's how we have an idea of how subduction zones work, is because, okay, the ocean's obviously involved here. So that's pretty cool. But what else? Oh, we're talking about the oceans. We're not talking about a lake here. We're talking about the seas. So we are looking at salts. So salt is going to bring in our sodium, which probably just mixes with the magma and starts to create some feldspar, right? We've got some sodium-rich feldspars. So again, some of these elements are going to contribute to the minerals that are going to form from the magma itself. But what else is in salt? Chlorine, right? Salt is sodium chloride. So we have chlorine. And chlorine is also a very poisonous gas. So when we have a volcanic eruption, we've got lots and lots of steam. That's going to build up most of the pressure that causes these volcanoes to be so extremely explosive. But they also have poisonous gases such as carbon dioxide and carbon monoxide, both mostly from the cooking of plankton deep in the subduction zone. We have chlorine gases, which are why a lot of volcanic eruptions are kind of green or yellow. So chlorine is a poisonous gas as well. We have sulfur dioxide, also kind of as a byproduct of what's happening and with the biological stuff in the oceans. So we're getting all these poisonous gases along with that steam. This is a subduction zone where there's a lot of active stuff going on. There's a lot of active volcanoes. All these little triangles here are volcanoes. So yeah, we have a lot of earthquakes because that's what we have whenever we have plates moving. But because of the subduction zone, we also have active volcanoes. So a lot of the most active and dangerous volcanoes on Earth are in Indonesia. So this is a very active plate moving all the time. After this 2004 event, a submarine went down to see how much the plate or the ocean floor had shifted, and found that the overlying plate popped up about 60 feet as the subduction zone drove down, or the subducting plate drove down a bit more. So yeah, plate tectonics is slow, it's deep, it's stuff we can't see all the time, but earthquakes and huge shifts of rock are, some effects of it. But what kind of volcanism do we get? Well, this is Mount Pinatubo from the Philippines. Huge volcanic eruption back in 1992, I believe. And this is the same kind of volcano we're talking about. We have a lot of water, so steam, and other poisonous gases building up behind this magma. Here we go. We have our divergent plate boundary. And again, this is going to be where we have our decompression melting. So solid rock, right? Rock is solid in the asthenosphere, begins to rise. It begins to expand. And it's still hot. It's not really cooling down that much, but pressure is being released. And that's enough to get this hot rock to go ahead and open up and begin to become a liquid, okay? So then it comes up here to our spreading ridge and begins to form the oceanic crust. Don't really see a hot spot. Oh yeah, here's a hot spot. So in this case, again, we have heat coming up from the mantle, for whatever reason, and it's going to heat up the oceanic crust over top of it and cause it to melt and cause that to rise. And that's pretty simple. That's, again, just like our having a pot on a stove. Okay, now where it gets fun, though, again, is at subduction zones, because we have our subducting plate here. We have our water getting in here. We have our organics, so we have our CO2 that's going to form as well. And you're working on a diagram like this in lab this week. But check it out. This is basalt, right? The oceanic crust is made of basalt. Again, back from the first exam, we got that. Basalt oceanic crust. So as the stuff melts, we are creating mafic magma, right? Basalt is a mafic rock. So we have lots of iron, magnesium, all that. Well, let's go back to Bowen's reaction series. We have our mafic magma here that's beginning to form, but that magma is going to rise and cool. And as it cools, we have different minerals forming out of that melt, crystallizing and staying down in the magma chamber, while the rest of the magma, which is still molten, continues to rise and fuel that volcano. What materials are going to solidify and drop out first? Well, olivine, augite, maybe some hornblende, but hornblende's weird. We'll get into that too. So our ferromagnesian or mafic minerals. So what elements are we losing? We're losing iron and we're losing magnesium because those minerals, the minerals that these elements make up, are crystallizing at a hot temperature. And so this mafic magma is going to kind of sit here and assimilate into the crust, but it's going to continue to cool. So as it cools, well, we've just lost a bunch of iron and magnesium. You know what we have a lot of though? We have a lot of silica because we haven't lost much of it. It doesn't take much silica to create olivine and augite. We haven't lost much silica. So this magma, this resulting magma chamber has become more enriched in silica, not because we added any, but because we removed a bunch of other elements, okay? So if this is weird, and I know it's going to be weird anyway, but if this is really confusing, go back to the other presentation called How Do Rocks Melt? I'm sorry, How Does Magma Freeze? That talks about magmatic differentiation, fractional crystallization, Bowen's reaction series. That's what we're looking at here. So go back, check that out. The Skittles lab that you guys did with Rachel, that's a really good way to kind of figure it out too. So our Skittles, we're ending up with red and white Skittles here. There's no white Skittles. She used Altoids, I think. But anyway, we're ending up with those guys. Okay, now we have a lot of silica in this magma. So we're going to end up getting a rock called andesite, which is intermediate, or maybe a rock called rhyolite, which is felsic. That's pretty cool. That's how we end up with those kinds of rocks. And then any granite, any magma that sits here and solidifies in the continent is going to create diorite or granite, intermediate and felsic coarse-grained rocks. Well, that's fun, but it's not done there. This magma has a lot of silica. Silica dictates the viscosity of magma. So this magma has gone from being, remember the ketchup and the peanut butter and the taffy from last week? This magma has gone from being this ketchup-y type of viscosity, which is what we get in mafic magmas, to becoming thicker and thicker. So we end up with like a peanut butter kind of magma here, maybe even for this guy, like a really thick oatmeal or like a taffy type of viscosity of magma, because this magma is so enriched in silica that it becomes more and more viscous, more and more thick. It doesn't flow easily. So any gases, any gas bubbles that want to move up through it are not really going to be able to. You can blow bubbles a lot easier through a cup of ketchup than you can through a cup of peanut butter. You could try it. I bet that sounds gross, but you can try it. So if we have all those gases, and we just talked about, yeah, we've got loads of gases coming down here in our subduction zone. If we have all these gases and we have this really thick magma that doesn't allow for the passage of those gases through it very easily, what happens? We build up pressure, build up pressure, build up pressure with all those gases, that really thick, you know, taffy-like type of magma, until we end up with huge volcanic eruptions. So that's another reason, the final reason, I guess, why our subduction zone volcanoes are so explosive. We're not just dealing with those gases getting down in there. We're also going through Bowen's reaction series because we have a very deep magma chamber. Check out this magma chamber, all the way down in the subduction zone, all the way up to the volcano here, very deep. There's a lot of time. There's a lot of opportunity for that magma to change as it rises and become more thick, more enriched in silica. If you look at the magma chamber at a spreading ridge, I just drawn a bunch of circles, I'm sorry, or especially a hot spot, there's really no opportunity for that to really change all that much. It's mafic, you end up with mafic rock and mafic volcanoes. End of story. Nothing too exciting going on there. But at subduction zones, we have Bowen's reaction series going on. So we have a lot of different things going on. Also, I mentioned, yeah, because of Bowen's, we end up with this really thick, high silica, intermediate or felsic magma fueling a volcano, but also the surrounding continental crust, which again is largely granite, so lots of silica there made up of felsic minerals, is also going to melt and get themselves involved in this stuff too. That is called magma mixing. We try not to use jargon all the time in geology. Magma mixing, not too bad. So we end up, may even get a thicker, much more viscous magma because of that happening as well. About the volcanoes that we get. So now we're talking about some volcano types. So the volcanoes that come from our oceanic hotspot tend to be shield volcanoes. We're just dealing with heat. We're creating mafic magma. So we just have nice, broad, but fast and pretty, can be pretty dangerous, very fast catch-up like lava flows, but they don't really tend to pile up a big, nice volcano. Well, no, these are the biggest volcanoes on the planet, but the lava flows are just so broad and they continue across such a wide distance, but then they do build up vertically. These are called shield volcanoes because the Hawaiian volcanoes look like warrior shields lying on their back. They're very broad structures, and they are the biggest volcanoes in the world. And if you go back to the, think about the plate tectonics lecture from a couple weeks ago, the biggest volcanoes in the solar system. Olympus Mons on Mars is a shield volcano. All those big volcanoes on Mars and the moon are shield volcanoes. Okay, so we have, we'll just kind of continue down the list here. If we have a really felsic, thick magma, we call that a volcanic dome. And so that's forming right now in Mount St. Helens. You can kind of see it here inside there. I can kind of show it a little bit with my pen. Cinder cones and shield volcanoes can have a lot in common in that they often contain both mafic lava. The difference is a cinder cone volcano, like this one here in Nicaragua called Cerro Negro, which has been erupting almost constantly since the late 1800s. These are places where there's a lot of gas. So I mentioned before that bubbles can move through a cup of ketchup easier than they can through a cup of peanut butter, certainly, but you're still going to get a mess. So do that. Take a pint glass, fill it with ketchup, stick a straw in it, and blow a bunch of bubbles. What's going to happen? You're going to get a splatter. We often call these splatter cones. So this is our thinner, more mafic type of lava, but there are a lot of gases building up, right? The big guys here. So a stratovolcano, sorry, I didn't mean to kind of cross that out there. Stratovolcanoes, also called composite volcanoes, because they're kind of mixtures of a lot of different things happening here. They can have lava flows, long, broad lava flows, but they also have extremely explosive behavior because a lot of the magma in here is highly viscous. It's intermediate or felsic composition. So we get those gases building up. Stratovolcanoes or composite volcanoes tend to form almost exclusively at subduction zones. Just call it a subduction zone volcano if you want, that's fine. But what's happening is that this material is so thick that the gases build up behind it, cause big explosions. But during some other periods of time, you can also have some broad lava flows as well. So they're called composite volcanoes because we have a mix of pyroclastic, which means born of fire, and also lava flows. So a bunch of stuff going on there. Finally, a caldera. The biggest, okay, I don't know if it's the biggest, but a big caldera is the one in Yellowstone National Park, where we didn't even recognize it as a volcano until the 1980s because it's so big. But this was where a volcano had blown itself apart, and we have this huge, area that is inside this big national park. Something that looks a bit more like a volcano, or the inside of a volcano after it exploded, is Crater Lake. Craters are smaller, though. This is technically a caldera. But Crater Lake in Oregon exploded when Mount Mazama, about I think 12,000 years ago, I need to check on that, erupted, and the inside magma chamber was emptied so rapidly that it just kind of sunk in on itself. So it filled up with rainwater. It's a beautiful place, Crater Lake National Park. So that's kind of not really a type of volcano, but kind of more an effect of what happens after a big one, usually a stratovolcano or a volcanic dome, erupt very drastically. The type, first of all, felsic magma, the highest silica content and therefore the highest viscosity, so like very thick oatmeal or like a taffy. It's going to form if it explodes, so if it's an extrusive igneous rock, like a lava flow, it's going to form something called rhyolites. So we can also call this rhyolitic, that's fine. And again, volcanic domes like this one, there's a bigger picture of the one inside Mount St. Helens. And they tend to form at continental hotspots like Yellowstone or subduction zones. So we need to have a lot of silica involved, and we can only do that if we melt continental rock, which is what happens when we have a mantle plume or hotspot under the continent. We're melting granite. It's still going to be granite magma. It's not going to change composition like that. Or subduction zones where, as we just talked about, that magma becomes, while it is mafic, deep, deep, deep in the subduction zone, it goes through Bowen's reaction series and becomes more intermediate, maybe even felsic, by the time it makes it to a volcano. Okay, then we have our intermediate types of lava, and this is going to create a rock called andesite. Andesite, wonder what that's named for. Well, it's the Andes Mountains. So remember, this type of magma and these types of volcanoes and this type of, very thick magma is going to form in subduction zones like the Andes, where we have the Nazca plate diving down under the South American plate, creating the Andes Mountains, which are a bunch of composite volcanoes or stratovolcanoes. So this is kind of our medium viscosity magma that, again, just like the felsic stuff, allows gases to build up behind it. But in subduction zones, that's where we have most of our gases. So these volcanoes do tend to be the most explosive on Earth because, unlike with continental hotspots, where do you get those gases from? Subduction zones are full of gas, and now we know why. All right, and then finally our mafic lava flows or basaltic lava, and this is going to form our broad shield volcanoes like Hawaiian volcanoes, or this is a picture of one of the Galapagos Islands, which are also forming at a oceanic hotspot. And this is, again, Cerro Negro in Nicaragua, a very explosive, very active, and actually quite large for a cinder cone volcano, volcano there. This viscosity of this lava, very low. This is going to be, we like to compare it to ketchup or honey. We can actually go up to a Hawaiian volcano and watch it exploding and watch this lava. We can't do that with other volcanoes. You don't want to do that with these other guys. And where this is going to form, think about where basalt forms. And if we ask you in class, which we certainly will, or lab, where does basalt form? You got a few places. Oceanic hotspots, because you have oceanic crust. It's already made of basalt. You heat that up, it rises, doesn't have to go too far, it's not rising enough to go through Bowen's reaction series at all. So it rises a bit, makes its way to that volcano. We just have basalt lava flows. We're just recycling basalt. That's what an oceanic hotspot's all about. Or spreading ridges, divergent plate boundaries, where we do have that ultramafic, the mantle peridotite down there that's rising, and by the time it makes it to the surface, we've got our mafic lava, which again is going to cool and form basalt. So on. So there are definitely some pretty hard and fast rules you guys want to be kind of familiar with. Okay.